Okay, good morning. We will continue with the derivation for 2D elasticity problem. Okay, so 2D elasticity or structural analysis basically. So if you can formulate the problem for 2D, you can also do it for 3D as well. Okay, so the idea here is to just to know the procedure, and accordingly we can go ahead with that. Okay, so equations remains the same, you can extend it easily. Okay, so although we will cover 2D only, you can easily extend it to 3D. Okay, it's up to you to do it. Okay, okay, now so far the story is you have a plate which may be fixed somewhere, there may be some forces somewhere, right? Some forces applied. If it is not fixed and no force applied, that really means force equal to 0 is applied. Yeah. Okay. So you have a domain omega, you have a boundary, say gamma u. So u equal to u bar, meaning that this is equal to u bar is given at gamma u, and then the rest is gamma t we call. Now gamma t itself may have gamma t1, gamma t2, gamma t3. At t1 there's different force, at t2 gamma t2 different forces applied, right? You can have various forces applied, right? So you can have, let us say from here to here is no force, from here to here there is some force which is applied t, there is again from here to here no force. It's possible. So in general we just write, what do you write here? The force is applied, and you have to write, so you write in terms of what you call it, the traction, right? So this traction is given, so you will write T is equal to T bar at gamma T. There the what T is, T we find out, so T really means the force is given. Actually it's just the force is given, nothing else. Okay, it's something like, see, example you take, for example, right? So you have to the plate, and here there will be forces like this applied here, right? So what you have in this case T bar, if you say like this is the traction given T is equal to nothing but there is some, this is distributed load. This say the traction has the same unit as sigma basically. So T is basically total force in x direction divided by area. Area is from, let us say from here to here is a b, so you write divided by b, and there is 1 is the thickness, so 1, right? So this is T will be, this is equal to this, for example. So this is how traction is nothing but this is basically net force we are talking about at that surface. Yeah, you got it? So this is what may be given. There may be some forces that T will have two components, equally Txi plus Tyj. That really means you can resolve each of them into two forces. So let us say our xy system is like this, x and y. So if this is T here, so you have from here to here you have Tx, from here you have Ty. That's what it means. How the forces are given. In any structural problem, what do you have? You have some displacement given and some forces given. The same way it is also given here. However, you write it differently. You also write it in a matured way. This is how you write mathematically, basically. Yeah. And here we know that we call it tau. Remember tau, and then n is equal to, we call it T, and where we had sigma x, we wrote sigma x, but it is, we can also write sigma xx, so sigma xx. sigma yx, that's what we wrote, then sigma xy and sigma yy, right? And multiplied by nx and y. As you know, nx and y is nothing but a unit vector perpendicular to the surface. So this is what n is. Right? This is n unit vector perpendicular to surface. So this n is nothing but nxi plus nyj. So all those things we did yesterday. So this is equal to is how tx and ty is related, and this is given, and which relates to the internal state of stress. Right? This is how the tensor and the normal to the surface related to the traction at the surface. Yeah. So this one is given basically. This you know from the geometry, so you know that, and this is what the state of stress at that point, right? So on that, basically you are applying a condition on sigma itself. That really means you are applying condition on sigma. The same way we did earlier there also, right? We applied in one. Do you remember? We applied a del u over del x. On that you applied a condition. Somewhere it was given. So what is this? This is sigma only, no? On sigma you had some condition applied, some boundary condition was there. Here also on sigma only you are doing, but only thing is this is now 2D problem, so tensor comes into picture. That's the only thing here. Yeah, it is not a single sigma xx. Here you have three different. We'll find out what is the meaning of that. So we have, so far we have this, the problem is given, and this problem we had what we call it a strong form, and the strong form we found, number one was del sigma xx over del x over multiplied by sigma yx y, right, plus, not minus, plus dx is equal to 0. This was the first equation. Second was sigma xy del x plus sigma del sigma yy del y plus by is equal to 0. So this is what the strong form, this is what the equation you have to solve. But this differential equation, it has a system equation. There are two equations you have to solve simultaneously. There is a connection between the two. And what is the connection? This is the connection basically we will see in detail how they are related. They are not independent. Why? Because these and these are the same. We will find out why they are same. Okay? They are connected together, hence you cannot solve it independently. And so what is the final equation to be solved? Solve this. Subject to this. This is the boundary condition is given. So solve this subject to this. This is what you have to do. Now, only thing remaining now is how to put in terms of u now, right? So you know that main variable here is a displacement, and in this equation displacement is not appearing. So how do we know? When we have to solve for displacement, displacement has to appear here, but displacement is not there yet. Here we are writing the boundary condition displacement you apply, but how will we apply if u is not appearing here? Sigma is appearing here for natural boundary condition. You have which is given here, so these will repeat, relate to sigma there. So far so good. Any questions so far? Okay. Now the next thing is, first let's simplify this one or see how they are related, how sigma x, y and sigma yx are related, right? You may be knowing already, but still we will write. So we have, as we wrote yesterday, we wrote sigma x, but let's write sigma xx. Then we have sigma yy, but we will write also sigma xx del x dx, sigma yy plus del sigma yy del y dy, and then you have shear terms. Okay, so this one okay, so this and this, yeah, so here we call it is on face y in x direction, right? Face y in x direction, right? So sigma, right? And this is sigma yx plus del sigma yx over del y dy. So similarly, this one is sigma on x direction, on x face in y direction, sigma xy plus del sigma xy over del x dx. Okay, and then of course we had b xy within it, right? Okay. Okay. Now, what we can do is about this point from in the middle, we can take a moment. So we took earlier the forces in the two direction, and what you get this one. This one is what? It is equation of equilibrium only. And it is coming from the Newton's law. Newton's law of motion. Second law, because acceleration is zero, so you are making all equal to zero. Yeah, summation of forces is equal to zero. That's what it is telling me, right? So this is equation of equilibrium only in x direction, y direction. But we did not see what happens to the moment, right? Moment is something that we also have to consider. It has to balance that way. So let's take moment about the middle of this element that we took, the test piece, and what happens? These all forces are passing through this. So basically there is no moment created. Rest will be because of all those. So let's start with from this side. So we have a sigma xy anticlockwise of plus multiplied by from here to here is dy, right? So you have dy here dx here. So dy, sigma xy multiplied by dy multiplied by 1, thickness is 1. Yeah, multiplied by from here to here is dx over 2. Got it? So we have that. Then minus this term. So sigma yx multiplied by, again we have dx multiplied by 1, and then you have distance from here to here, which is dy divided by 2. So we have that. Okay, then look at this one. So this is also anticlockwise. So write plus sigma xy plus del sigma xy over del x dx. multiplied by again dy into 1, and this lever is dx over 2. Yeah. Then we have this also, the top one. So that we have sigma yx plus del sigma yx over del y dy multiplied by dx multiplied by 1 multiplied by dy over 2. Yes, we are taking total moment is equal to 0 you are making, right? So this is what it is. Because of bxy there will not be any forces moment because it is distributed. I mean, there may be because of that also, so but here let's assume this is a constant over it. Okay, so if it is very very small, we can assume that this is constant over it, and because of that there is no moment created because of bxy basically. Yeah. Okay, so what we have this is that is equal to will be equal to 0. Yeah. Then what do you get? We have sigma xy, so equal to 0. That means we have sigma xy, okay, and then this plus this, right? So we have 2 sigma xy here, if you see here, right? So 2 sigma xy
dx by 2
plus dx dy over 2. Okay, it will be just this one because half coming from here, half coming here, you add them together, the sigma xy dx dy. Okay, then what do you have? Similarly, you have minus sigma yx, and then similarly you have dx dy coming from here minus, and then here. Then we have, if you see here what terms are coming, the next term will be plus del sigma xy over del x, and then half then dy, then half dx square terms comes. So higher order term we are getting, right? Dx square term we get, and similarly we get minus sigma L sigma yx del y, then you have dx multiplied by half and dy. Okay, so higher order term, as we always do, we neglect it. We say they will be higher order terms, so make those equal to 0. Basically, all is equal to 0, and hence, what do we get finally? We get this sigma xy minus sigma yx dx dy is equal to 0. That tells you that sigma xy equal to sigma yx. Actually, both are same. Yeah. Okay. Well, all those things you already study in theory in solid mechanics. Yeah, for undergrads. So actually, on that level, we study it. Still, we repeat it here. Okay. So that you recall it, you basically you can make connection. Whatever you studied there was not a waste. So still it's applicable. Okay. Okay. It will be applicable the whole life if you stick to this area. Now sigma xy equal to sigma yx. If you write that, then definition of all these things you can change. So this becomes sigma xy, sigma xx, sigma xy, sigma xy, sigma yy. You can write like that. No need to write yx, xy. No need to write here this equation as yx here, and so we can, this equation itself we can write as del sigma x x del x plus del sigma xy, right? Del y plus bx equal to 0. Yeah. Then you can write del sigma xy over del x over del sigma yy over del y plus by equal to 0. Because both are same, you can write that way. That really means the yesterday we defined sigma x as equal to sigma xxi plus sigma yx. Remember yesterday we did this plus, so sigma sigma x was this plus this basically, right? This x I plus j. So sigma, we wrote sigma xy, right? So sigma x, sigma xy, j, right? Yesterday we wrote like that, right? For we combined them together and we wrote as a single force or a stress, right? Because they are not really a stress. This is in terms of force basically. When you say stress, it is assumed to be either perpendicular or tangent to the surface. When you combine them, you're talking about something else. You're talking about the force basically, right? If you multiply by the area, it gives you the force in some direction. It is not a stress, but you are writing. There is a quantity called sigma x. You take it as this, which is defined this way. Now sigma y is same way. Sigma xy I plus sigma yy z. Yeah. So yeah. So these now can be written based on this. We can also write in terms of divergence, and we love divergence. You know, this you can write as sigma x equal to bx equal to 0, and divergence of sigma y vector plus by is equal to 0. We also can write like this. Yeah. So this follows from here. This is we did the simplification basically. We are making it more elegant basically. You are writing more matured way. Yeah. Okay. Now we can also define sigma vector. Sigma vector itself, we can define it like sigma xx, sigma yy, and sigma xy. You can now define like this. This is the sigma is a tensor, but you know that in that tensor, these two are the same. You can also represent it as a vector. It's a mathematically basically. This is mathematics basically. You are, for convenience you are doing it. Yeah. Otherwise, you can also formulate in tensor, but tensor mathematics becomes even more difficult. So you reduce it to the only 2 dimensions, meaning there's a matrix formulation rather than a tensor formulation. So sigma equal to sigma xx, sigma y, sigma xy, and this equation also we can write differently a little bit. And how do we write? So the same equation, this equation, we write it as, how do you write? So here there is a matrix, then we have sigma xx, sigma yy, sigma xy, and then you have bx, by, so we write here bx, by, and this we have equal to 0, 0. Now fill in the blanks here. Yeah, we are now writing the both things in single equation, right? Although it is a matrix vesicle, but yes, still both are together. We are writing. That's what we are going to do, right? Single equation, we can combine them together. So if you see here, how do we write it? Here we have del over del x. Now second is 0. Then del over del y. Right? What is the next one? Here it will be del over 0, del over del x, del over del y. That's it.
Del over del y, del over del x.
Yes, yes. You got it. Okay. Now we define del S as this one. So del over del x, 0, del over del y, and we have 0, del over del y, and then del over del x. We define this like this. Okay, so this is del S transpose of this, whatever you are seeing here, transpose of that we define del S. Yeah, so what do we get? Final equation becomes, from here we write del S transpose of that, and then sigma plus V is equal to 0. So this is in one short notation. You can write that, where you know that yesterday itself we defined this equal to dx and dy. Okay, in case we did not define, this is how it is defined, right? So a small format but powerful one. See, it captures the everything. Whatever we did yesterday till now, it captures everything right there. Yeah, so that's why it is so powerful, especially when you are writing research paper. This kind of things you write. That's it. You don't have to explain anything. Yeah, and then you write that subject to the boundary condition. Boundary condition you define like this. That's that. Rest is mathematics to solve it. Once you define this is the problem you have to solve, rest mathematics will do it. Yeah. Okay. This is your strong form. Okay. Of course, you write subject to u. Now we don't know as yet at gamma u and q, not q but t is equal to t bar at gamma t. So this is the whole structural problem that we need to solve. Yeah, so any question, guys, so far? Now all steps that we have to take now is to just make sure that we are able to solve it, and accordingly we will do it. So in order to solve it, what we need to know? How sigma is related to displacement. Do you know how it is related? It is not directly related. It is related through strain. We know the sigma and strain, stress and strain, sigma and epsilon are both are related. And epsilon, you know that epsilon has u term there. Yeah. So first we will convert sigma to epsilon, and then we will convert epsilon to u, right? And then we will do it. Right? The same way as you did it for 1D problem. This is just 2D problem. Hence, we have a bit complicated. There was a case when there was one student from computer science, and being associate dean of UG, I get some time to talk to UG students, and he was afraid that he will not able to perform. So last semester he did not do well. And he was saying he wants to change branch so that he can complete other branch, easily. Then I told him, you are already in computer science, and this is the easiest branch you are in already. There is a truth. Mechanical is very difficult. You understand the equations, physics, mathematics, so much involved. Computer science is too easy. I mean, it's not my statement. You talk to their professors. I talk to my good friends there, and they agree with it. So this is because of all the mathematics, all the physics which are involved. It should be other way around, basically. Those who are, like all India topper, they should take mechanical basically. Of course, it's a job market. Regardless of what you do, if you are good, paid well, then you take the job. Whether it's an Excel sheet you are putting in, adding A plus B, if you are highly paid, you will take the job. That's the thing. So, I mean, it's not you, but everybody does the same way. Not everybody. Means you later on you realize also, and then you think about it. But the thing is, you see, in like we have a lot of things to deal with, mathematics and all. Yeah, so it's not only mechanical, electrical, civil, all those have multidisciplinary subjects. So this is not single science which is involved. You have to see the physics should be valid. There's a chemistry which is valid. There's some biology also there that has to be valid, and so on. There's a lot of multidisciplinary. In civil, even you have a geophysics coming into picture. So it's a very multidisciplinary, and hence you have to take care of a lot of things. You have to learn a lot of things. There's a lot of subjects there. So, and if you count the number of subjects in computer science, it's much less. There are a few core things that you do and do it. I'm telling you because I have myself coded and all, so it's not that I'm just So I already basically I have done all kind of things, and hence I'm talking about. Anyway, not to offend anybody, but meaning that it is expectation. I'm telling you, being in mechanical like departments. Like you have to think about lot of a lot of mathematics which are involved in it. So if you go into CFD, for example, even more complex problem you are solving and all. So finally, every department has its own contribution. But it's not like that one department is easier than the other department. It is some scope in everywhere, and in every department you can do well basically. But you have to work hard basically, regardless of where you are. Anyway, so now coming to this sigma we are talking about. Sigma itself is related to the stress, to a strain, and we call it D. Sigma equal to D strain, where D has to be a matrix, where sigma is, for example, it will be sigma XX, sigma YY, sigma XY is equal to, there will be some D, we have to find out what, and then there is some strain. Let's call it sigma, the strain EXX, EYY, epsilon XY. Okay. Now D depends on type of problem. Okay, so all these I'm not going to derive it, otherwise it will be a solid mechanics. Already done a lot of things, but I will just write D, for example, for plane. Okay, spelling PLANE isolated should be plane, right? No, PLANE, plane is planar, right? So planar. So plane. Okay? Plane stress. If I'm wrong, let me know. Okay. PLANE should be right. Okay. So D for plane stress problem is given by D is equal to E divided by 1 minus nu square. Then you have 1 nu 0 nu 1 0 0 0 then 0 then what you have here 1 minus divided by 2. So this is plane stress you have like this. Yeah. Okay. And what do you have plane stress? Plane strain. Okay, you can check whether I'm correct or not. Plane strain. We have P is equal to E, and then we have 1 minus 2 nu. Then you have 1 plus 1 plus nu. Then you have 1 minus 1 minus nu, right? And this will be minus nu. Okay, here I think it should be minus nu, right? Minus nu here. Here, okay, it will be 0 minus nu, 1 minus nu, 0 0 0 0 0, and you have 1 minus 2 nu divided by 2. Okay, something you have to memorize, so let me check.
It's right.
Is correct?
First one is right.
Okay. Second one, just check second one.
So,
1 minus nu, 1 minus 2 nu by 2. P 1 plus nu, 1 minus 2 nu,
so mu is there.
1 minus nu. So there is no minus. Hmm.
And second one.
So there is no minus here, otherwise fine. Huh? हाँ क्या नहीं दिख रहा guys, are you able to see? Hello
Yes.
guys, are you able to see it?
Yes, sir.
So you see the board now?
Yes. Yes. Yes.
Is the blackboard visible?
Yes.
Yes, sir, we are able to see.
Okay. Thank you. Okay, so we have this relation which is coming from, you can derive it, you can study the solid mechanics for details, how you have proven all those, derive all this. Okay, now next is once you have that, we write like this one. So our this equation, you can write it as the equation of equilibrium, this T, and then you have, instead of sigma, we write D, and then we write epsilon plus B is equal to 0. So you also write that. Right? And the thing is, now sigma is gone. We have epsilon there, a strain there, and hence now next thing is how we derive the strains basically. So for strains, derivation is simple, and what do you have? You have basically the definition itself. If you look at, let us say you have one test piece, and you have let us say you have here at this point you have u x is the displacement. So from, let us say from x direction, right? So this is the displacement, you have ux, and here you have ux plus del ux over del x dx, right? So displacement here, if ux displacement here is this, so total length, or you say delta L, right? So from here to here is dx. Yeah. So initial length was dx. Change in length we are finding out. So change in length will be whatever displacement here minus whatever displacement here. That's it, right? So it will be ux plus del ux over del y dx minus ux, which is equal to del ux over del y dx. Fine. Now del epsilon x is equal to nothing but delta L over dx, which is del ux over x. Here similarly you can write similarly del epsilon yy equal to del uy over del y. Okay, and next is okay. So here we want to find out what is epsilon xy. Right? Epsilon xy is nothing but you have the angles. So you have angle here. Yeah. So let's say this is theta 1. This is theta 2. So simply this epsilon xy is defined as this angle theta 1 and theta 2 only, right? And this we have to find out. So if this is so basically this guy is del you write u, whatever you have ux and uy basically in this case. So you have from here to here this is ux, from here to here you have uy, right? And then what is this point? This one is, this will be
Integral.
This will be when it comes to
Dx
uh,
by cos theta.
it will have two displacements, right? In x direction, in y direction, right? So in x direction, it will be del ux plus del ux dx. That will be in this direction, and in an up direction. In this direction, it will be u y plus del uy over del x and dx, right? No,
Second by
not del y, no. This x, how it is? So x we have not, y we have not changed. In the dx only it goes like that. Okay, so what we want to find out? We want to find out this angle. The theta 2 will be equal to theta 2, assuming theta 2 is very small. Right? Theta 2 is very small. Right? So theta 2 is equal to whatever this height is. This height is what? This height will be u2 plus del u2 over del x dx minus u2, right? So total height, basically this is uy, this is uy plus this. So we want to find out this height, right? And divided by this, which is dx. So over dx. So this is the uy. So theta 2 is nothing but del uy over del x. Similarly, theta 1 is equal to del ux over del y. Similar analysis you can do, you can find exactly the same thing. And hence, epsilon xy is equal to theta 1 plus theta 2 is equal to del ux del y over del uy over del x. Yeah. Any question? Now can we write epsilon xy in terms of ux and uy? Right? So you can have u, you can write it as ux uy like this, and then epsilon tilde, which is equal to epsilon xx, it's epsilon yy, epsilon xy. We want to write something here, and then we write as ux uy. Okay, so we want to relate it. As you know that we will use that in the equation, so that when we solve for ux and uy only. And you can see from here that if you have Ln xx equal to del ux over del y. So what will we write here? Del over del x and then 0. Since it's 3 by 1, so it has to be 3 by 2. This will be 2 by 1, right? So this is 3 by 1. Next is what? Next will be 0 del y. Third is del y here, del x. Or simply epsilon tilde is equal to this we call s tilde, and then you have u. Right? Okay, so we can write this equation now. Original strong form is nothing but del s transpose d tilde, then del s tilde, then u tilde plus b is equal to 0. Now it relates to u now, right? And now if you say that boundary condition, if you write u, here you can write u bar also. You can also you can write this is equal to some, right, at gamma u, and now next is we have to write this is equal to t bar. Again definition remains the same at gamma. The definition of t tilde we have defined already, so we confirm the same. This is the whole story as far as the strong form is concerned. Only thing now remains is the weak formulation and solving. Yeah, so that we will do in the next class. So any questions so far? Anything that you could not understand? Luckily, all these things have been done long back by a lot of people. Those days when there was no boundary between mathematics and physics and chemistry. So the same people worked on different things, working on something, but he found out something else. All kind of things happens. So you can see in mechanics. Actually, mechanics is some. I don't know whether you had, like in +2, mechanics is part of mathematics also. You remember statics dynamics? Did you have in +1, +2? No. But even like statics dynamics is taught as a part of mathematics. So it's a lot of mathematics there, no? I mean, few definition comes from there. When you say like eigenvalue problem, for example, right? So when we wrote this tau, remember tau, and we did n is equal to, we have some t like this, right? So tau is a tensor, then you are multiplying within a vector, and then you have some vector coming. What if this t is nothing but equal to a gamma, which is a scalar, and this n itself? It's possible, no? It's possible that this fraction is such a way you multiply a scalar to the unit vector, which is perpendicular to the surface itself, then what happened? This is equal to this. T n is equal to gamma n. And this is a eigenvalue problem. So initially people who did this then realize, okay, so what is this meaning of that? And then once you reach here from physics, you take it as a mathematics problem and you go from there. But origin is what? Physics. In all cases, whenever you needed, then only you did it. It's not that just realize, okay, there's something called eigenvalue, so I have to work on it. Nobody did like that. So when you are working on something, then realize you do it. And hence, this tells you n, here n is what? If that is the case, in mechanics, what is the meaning of n tilde? N vector. N vector we understand, but from solid mechanics point of view, principal directions, right? Principal planes basically tells you the. It defines the principal planes basically. N is the perpendicular to the principal planes, right? And this, what is this? Lambda. What is lambda? Principal stresses. Comes from there only. Yeah. So this is how they are related. So mechanics really, I mean, lot of things I have mathematics there, but if you see mathematics in your problems in physics, it's exciting. I don't know how you feel, but okay. All this also comes from continuum mechanics. So advanced solid mechanics that MT students study here is also partly has continuum mechanics, continuum solid mechanics basically. Yeah? So this also is there. Continuum mechanics is something that you will see there's no difference between solid and fluid basically. So you treat the same way. They have different constitutive law basically based on that they separate out. But definition of forces, shear forces or stresses, all remains the same in both the cases. Okay, guys, any question? If not, then I will see you guys on Monday.